now the plan is to talk about, continue a little bit what we started with the notions of LQ norms. And in particular, we will concentrate today mostly on the L2 norm, which is an important space to consider for us. And the basic idea here is that in order to go into the Fourier analysis side, we need to understand somehow the notion of an angle between two functions. Somehow that we could say that two functions that we are considering in our analysis have a certain angle in between them. For example, whether they are almost orthogonal, pointing to different directions, or whether they are basically parallel. And the reason for this is that this allows us to understand the kind of Fourier basis for these functions, whether they are really orthogonal to each other or whether they are parallel. And then we can maybe use some basic ideas of, for example, from linear kind of analysis or vector analysis to be understanding these properties. And that's why we need to talk about the notion of inner product, for example, which allows us to then talk about the angle between two functions in a more, maybe a bit abstract way, but it will be useful. So the kind of basic property that we want to define, so let's maybe call it the L2 theory, which is the main kind of thing. A little bit at the end I will mention about the LQ norms, like the analog of this in that setting. So we need to define the notion of an inner product of two functions. So let's take let f and g be two functions from zb to c, and when we can just basically then define that f, this bracket notion, to be equal to the sum over the group of ft, and then you take the complex conjugate of the other function g. So remember, this is the complex conjugation. The reason we take the complex conjugation is that then this implies that if you take the same function f and f, and if you compute this t in zb and take ft and ft here and its conjugate, then the nice thing about the conjugation is if you take the product of this complex number with its complex conjugate, then you just get the norm squares here. So basically you obtain here, this is the modulus, so ft squared. So that's the reason why we want to define this. So this is the inner product of two functions. So thus, if you remember the definition of the L2 norm, so thus the L2 norm of a function, so this is by definition, this was, if you remember, the sum of t in zb ft squared, and then you raised it to the power half. And this is, by this notion, it's just equal to f to the power half. So so basically you have this kind of formula that the square root of this inner product with itself, it gives you the L2 norm. And vice versa, if you take raise to the power 2, then you get to that notion. So this is kind of important. This allows you to now talk about the L2 norm has this kind of connection to notion of an angle. In some sense, you could talk about the notion of the angle. So now, for example, you can see that if you kind of visualize this. So let's visualize. So visualize the inner product. Then what you end up seeing somehow is that if you start from, let's say, you could think about your function f to be, it actually is a vector, because it's a complex valued vector. So if you think about this function f from zb to c is identified with as a vector in C to the power p, because for every point in the group you're associating a complex number. So you can think about f as a vector V in like CP. So then the inner product is just basically the typical inner product in CP. So you could think about let's call it that it depends on this F. So then you can think about that if this is your vector in CP, that it has certain like angle, then the inner product like telling if you have another function, for example here, this would be some other corresponding to some other function, Vg, this could be now in CP, then you could then, for example, talk about whether they are orthogonal. Whether these vectors are orthogonal, then that means that the functions are orthogonal in this sense. And the inner product, that would mean, this would mean that the inner product of f and g has to be equal to 0 if you have the right angle here. So if you do this in infinite dimensions, there are like courses that maybe deal with more like this infinite dimensional theory, like harmonic analysis, basic harmonic analysis courses. You have the same type of an intuition going on here, that instead of like, because now you have infinite dimensions, so you can't think about things as, let's say, elements in this kind of nice Euclidean space, basically, but actually you have to go to this more like infinite dimensional space. But in there, you can still like think about them as vectors, kind of like more like an infinite dimensional vectors that have, you can talk about the orthogonality properties, for example. And now if you have non-zero, if the inner product here, for example, would be non-zero, then there would be some angle. So then if they wouldn't be equal to this 0, like, I don't know, like an angle, then this angle is then, there's a formula using cosine of this angle, that, or example cosine or this angle, that you could then represent here. You would have that this is some non-zero number. There is some kind of an angle. Okay. The main example, for example, could be that if f is equal to g, then they are like parallel, because there's the same vector. They correspond to the same vector, so they're like parallel in this sense that you have. Okay, so this is kind of the basic thing about inner products. So now the reason why, the main examples that you usually encounter, and this is like the foundation of Fourier analysis as well. In this context, is we talk about these basic functions. I think I call them characters, and they are functions of this type. That is, let's call it chi k. It's a function from zb to c. So we have a fixed k in zb here, and we define this chi k t to be equal to the e to the power minus 2 pi I. These are like in the definition, if you remember from the definition of the Fourier transform, we have these quantities. Okay, and this is now defined, oh sorry, this would be t. Okay, and then t in zp. Now if you look into this, so recall that if you take the Fourier transform at chi, then this was equal to t zp, ft e to the power minus 2 pi I t k over p. So then this is equal to t in zp of ft chi k t. So it's these functions that you use to define the Fourier transform of this point. Actually, maybe I should maybe actually I'll use without the minus in this context. The reason for that is becomes later clear if I want to talk about this character. It's just I'm putting the minus here instead. So it's at the point. You could think about that this is at the point minus k. In the notes I'm using the minus, but actually it turns out that it's better to use not minus here. You get the same property in the end, that even if you plus or minus in the situation. I might actually edit this from the notes to have a plus there. The reason for that is that then you can actually write functions as a basis functions using these so-called characters that we have. So now we see that if you take the inner product of these characters, chi L, let's say inner product of two functions, then what you have here is that when you open the definition of the inner product, you get chi k t and chi k and chi L t, and then you take the complex conjugate, and then once you sum these up, you sum over the zp, this becomes e to the power minus, actually let's use the plus here, 2 pi I tk over p, and then this is e to the power 2 pi I tl over p, and then the conjugation of this one. So once you open this up, the conjugation of this number actually makes it minus, because it takes the negative number of that complex conjugation of this number, and so it goes down in the conjugation. So that's why you have t in zp, e to the power 2 pi I tk over p, e to the power 2 pi minus 2 pi I tk over L over p, and once you sum these together, you get this expression t in zp, e to the power, once you take the 2 pi I can actually take them all into 2 pi I, that's in the front, and I put the t as well here, and then I put k minus L over p. So now you have this expression that depending on what k and l are, they become this kind of a number. And now basically, depending on which numbers you have, so if k is equal to l, so you have two possibilities. So if k is equal to l, this is just summing numbers equal to 1, then what you get here is if k is equal to l, you're just summing ones of the all time, then this actually becomes p. I think that's what it is here. So I noticed that there is actually a slight error in the exercise 4.10. I'm using this, so there should be a p here. And then when you have the k not equal to l, then you can use the exponential summation formula again, and you can actually prove that this is equal to 0 in this case, because you're basically going a rotation of the space with angles around the space. So now if you would normalize this, so you can see that if you would normalize this by, so now this, if you use the chi k, I don't know, you could take, so, well, you could take this, that this implies then that this chi k is like orthogonal to chi L. You could say this is like orthogonal if k is not equal to L. And the reason we talk about characters is that they allow you to represent then more general functions as like sum of these two functions which you have. And so you have this kind of orthogonality of these two examples. So they go back to, you could think about them like basis vectors of all the functions can be written in the form of these two functions when we talk about the Fourier series, for example. Okay, so this is like the basic thing about orthogonality. And now the final thing that I wanted to talk about today is then the connection between the inner product and L2 norms. So we already know that, so we know that if you take the ff of the same function, we know that this is the L2 norm. Actually, you could take this as a square root of this. We already know this. But then there is this thing called Cauchy Schwartz inequality. Inequality that deals the case when f is not equal to f, so f is not equal to g. So you have something like this, that you can do a connection in this way as follows. So we let f and g to be any functions from zp to c. Then we can bound the, let's say, absolute value of the inner product, because this possibly could be negative number, and we can bound this by their product. So F2 and G2 we get in this form if we want. So that's the kind of like a basic notion of the that we are going to be using quite a lot actually later on in the course. So how does this help us? So let's prove this. You can see the proof is not too complicated, and basically we used like we may first of all assume that F2 is positive and G2 is positive. Let's call them, I give them names actually to these norms that we don't have to talk about them like to actually, well actually let's see this, so before we give the name. So let's just call them, we may assume that they are positive, because otherwise F is 0 or G is 0, so this implies that the left hand side is also 0. So this left hand side here on the thing, because it's an inner product, if one of the functions is 0, then of course the whole inner product is as well 0. So that's the kind of assumption we can do. So now finally, we also have the following property that kind of this is like basic property about the function. So if we have that a and b are non-negative numbers, then this implies, well, we know already that a minus b, if we take this, then this is at least non-zero, because they are real numbers. You're taking their difference to power 2, then you get non-negative, like a real number which is non-zero. But then this number here, this is a squared minus 2ab plus b squared. So this implies in particular that we move everything to the other side, that a squared over 2, if you divide both sides by 2, plus b squared over 2, this is at most ab. And this kind of an inequality is the basic inequality that we are going to be using to prove the Cauchy Schwartz inequality. So we just apply this with the following expression, that a is equal to, so we first fixed for fixed t in ZP, a to be equal to the absolute value of f over f. Let's take the L2 norm, and then b is equal to the absolute value of g and the L2 norm of g. So these are both non-zero. We can, because they could be 0 at some points, but we know that because the L2 norms are positive, we can actually do the division. So we know that they're well-defined numbers that we have here. So if we apply this inequality here with this a, then we obtain the following, that if we take the product of these numbers, we take ft f2, so this is a, and then I take g t g2, this is b, then by the inequality this is at most a squared, which then would be, if you open this up, it is ft squared over 2 f2 squared, and then plus, I think I have the gt squared to g2, so this is a squared over 2, and then this is b squared over 2. Okay, so now if we like basically open this up and move all the terms on the right hand side and sum over the t, we can do the following, that if you take this sum first and then move the terms, so we sum over t, we can actually take the expression on both sides. So actually, let me just copy this this whole expression. Take this here and then move this a bit. So we can sum over t in ZP on both sides and then sum over t in ZP on both sides on here satisfies this, because this above holds for every t in ZP. And now if you sum this over, we get here that this expression here, what this is actually equal to 1 over f to g2, and then you have the sum over zp of ft gt. Okay, and then what about this expression here? We can actually open this up. This becomes the L2 norms that actually appear here, because on the above here we are summing over these numbers of the L2 squared, and this is actually the L2 norm. So this becomes just a half plus a half, because you're cancelling out. So this, when you sum over the t, take the constant out in the front, which is the L2 norm, and the L2 norm of g, you get equal to 1. So, but what you have now proven is that t in zp of ft gt is then at most f to g2, as we said. And now why this implies the final thing is that now if you take the absolute value of f and g, we get that this is the absolute value of t in zp of ft gt complex conjugate. Then by the triangle inequality of complex numbers, that if you can take the triangle inequality, the finite sum of complex numbers, this becomes the sum of t in zp of ft and then gt complex conjugate, which is then actually equal, because the complex conjugation doesn't change the norm, so this is equal to fg gt as claimed. So we have the proof of the Cauchy Schwartz inequality as claimed. Okay, so that's the kind of basic idea how to prove the Cauchy Schwartz inequality. And we will later on we will use this in a for very specific functions that we have in our case. So in later on I will show you like how actually this L1 identity, the Cauchy Schwartz, is being used for some specific functions that come into play. This actually turns out that in our case, once we use the L1 identity, we end up from the L1 identity move to some inner product of two different functions. And then we later on we will apply then the Cauchy Schwartz inequality bound, the expression we want to bound into using L2 norms. And later on in the next week, I think I will talk about the notion of Herders inequality, which allows you to use the L2 norm and this vector space structure to go into the Fourier space. So we can then go in within the L2 norm to the Fourier space using the isometry of the Fourier transform between L2 norms. So that's very, very briefly like what's going to happen in a few lectures. But then I want to end this lecture, so this is the last thing, so on LP norms, just this final thing which is called the Herders inequality. That's the like final thing I want to I won't prove it, but it's kind of like the same kind of an idea that goes into the proof that if f and g are functions from ZP, let's call it actually LQ norms. I should maybe use different ones. So C, then we have that the inner product of f and g is at most actually by, if you take the f, it's q norm, and then g, it's q prime norm, where this is actually for every one. Let's take this q less than infinity, where q prime is the so-called Herder conjugate of q, i.e. we have that it solves this equation that 1 over q plus 1 over q prime is equal to 1. So you can actually solve it with this equation. And the Herders inequality is a way to go into higher order LQ norms. It's very useful to also connecting two different LQ norms to each other if you have this like information, especially when you talk about in random walks, if we want to talk about moments of random walks, like tails of random walks or more complicated events than just mixing events that we are now considering, then this Herders inequality comes into play as a quite important tool in those situations. And the proof is based on so-called Young's inequality for real numbers, which is saying the following, that if a and b are non-zero and 1 over q plus 1 over q prime is 1, then this implies that ab is at most a to the power q over, I think it's q, and then 1 over, this is b to the power q prime over q prime. Yeah. So it's a bit like, remember that in the case q is equal to 2, you have this a squared over 2 plus b squared over 2, which was the foundation for the Cauchy Schwartz inequality. So in the same way, you need this type of like a real number inequality to do this. So I will leave the details of this to an exercise for to do. Okay, so that was all. This was quite a long lecture compared to other ones, but this kind of went through one of the key theorems, which is the Cauchy Schwartz inequality. So I hope this was okay, and that's all for today. Thanks.